Hello, my name's Sam Stoddart, and today I'm going to be talking to you about the indirect comparison of treatments. This is a group of techniques that are emerging. They've actually been around for quite a long time, but it's fairly recent that they've actually become available for routine analyses, and that's because of some of the technology behind them has made it easier to do them than they were in the past. Indirect comparison of treatments, this is a branch of meta-analysis. So in order to talk about this, we're going to start off with looking at traditional meta-analysis. I'm just going to review some of the key features of traditional meta-analyses. That is direct meta-analyses comparing two treatments. And then I'm going to talk about some of the problems we commonly encounter when we're looking at doing direct meta-analyses. Following on from those problems, we're going to look at approaches we can use to get around them by using indirect evidence. Following on from that, we're going to talk about what I'm calling mixed treatment comparisons, but you also might have heard referred to as network meta-analyses. And when we talk about that, we're really going to be interested in how they are a generalization of indirect analyses. And then we're going to talk about the sort of approaches that I and my team use when we're working. So if we start off with a direct meta-analysis here. So this is a sort of traditional situation that you might come across. You have two treatments, in this case drug A and a new drug, and you want to compare them directly. You have several trials, WinBUGS et al., Smith et al., Jagan et al., Pietri et al. In our example here, and you want to in some way aggregate the evidence from those different trials into one summary analysis. In the example I'm using today, we've got 4 studies and we're interested in a continuous outcome. That just avoids us getting into some of the more complicated bits of meta-analysis involving log transformations and things like that. So for each of these studies we calculate an effect size, which I'm going to call D, and a variance, which is the square of the standard error in this case, because we're looking at sampling distribution of the mean. Now if there's any of that which is complicated for you, there are various other bits of training about sampling distributions and variances and things like that that are available, where we can go into that in more detail. For now, what's important is that you understand that the variance describes how certain we are of the precision of our estimate of D, our effect size. So to come up with a pooled effect size, we can't take just a crude mean of all the effect sizes we get from the individual studies, because those studies differ in terms of size, quality, and all sorts of different things like that. And as a result, it would be, so for example, it would be inappropriate to take a study with 1,000 patients and a study with 10 patients in it and treat the study with 10 patients as if the data it provides is as accurate as the study with 1,000 patients. So we have to weight our studies in some way. And usually we do this using something like the inverse variance method. So in this case, that just means taking 1 over our variance and using that to give a weight to each individual effect estimate. Again, we've got other bits of training available if you want to go into that in more detail. The key thing here is that because variance gives you some idea of how certain you are about your estimate from a given study, using the inverse of your variance gives you some indication of the relative weight that you should assign to that estimate. Okay, so what I've done here is we have a table with effect sizes, D, for each study, and variances for each study. These are just made up data, so don't concentrate on them too much. We also have the weight, which we've calculated as 1 over the variance, and you can see that. So for example, the variance here is 4, the weight here is 1 over 4, which is a quarter, which is 0.25. Our next stage in a direct meta-analysis is to multiply our effect estimate by the weight. So in this case of WinBUGS 2002, we'd take 3.2 and multiply it by 0.25, and that gives us 0.8. And we can then sum both the weights and the effect sizes times the weights, and we can use that to calculate a weighted average. So just to talk you through this equation, because if you're not familiar with the sorts of nomenclature that we use, this can look a little bit confusing. All this is saying is that our overall estimate of effect is produced by summing, that's what this sigma here means, our individual effect estimate, di, multiplied by our weight, weight I. So 3.2 times 0.25 is 0.8, so that is D1, W1. If we add all those up, we get this value down here, 3.00625. And if we sum all our weights, which is our denominator, we get 1.2625. And if we work out those sums, we get 2.381. So our weighted estimate of effect is 2.381. Now handily, we can also calculate confidence intervals around this estimate using the standard error derived from the variances of the studies that we've included. So to calculate that, we simply say that the sum of our weights is 1 over our variance. So if we, to calculate our summed variance, we just take 1 over sum of our weight. To actually get the sum of our standard error, we to get our overall standard error, we square root our weight, and that gives us 0.89. Then, using property of the normal distribution, which is that 95% of its total mass lies within 1.96 standard deviations of the mean, we can calculate a 95% confidence interval around our estimate. We can make this a little bit easier to understand by putting it all on a forest plot. So here's a standard forest plot produced using a traditional meta-analytic approach. So we've got each of our individual studies with their effect estimate, D, and confidence interval around that. And we see that none of these are quite statistically significant, but that when we take a weighted average, our overall estimate is both positive, and because it doesn't overlap 0, is statistically significant. And because we've done this in Stata, and it's produced a nice little weight for each of our as a percentage for each of our studies, which is quite useful because you can immediately say that, for example, Smith has contributed quite a lot of information to this analysis, whereas Pietri hasn't. Okay, so that's how we do a sort of standard traditional meta-analysis. Now if we move on to the problem that we often find, is that we have a new drug and we want to compare it to an existing standard treatment, say drug B in this case. Now because the requirements for regulatory submissions, it's usual to end up with a trial which compares your exciting new drug with some standard comparator, often placebo or some sort of standard of care. So in this case, what this diagram shows us is each of the treatments in an evidence network with lines showing where we have evidence. In this case, we have evidence for everything versus drug A. Now the problem is, if we want to compare our new drug to drug B, we don't have any direct evidence, so we can't do a direct meta-analysis. Now we could just do another trial of new drug versus drug B. The problem with that is twofold really. First of all, it's incredibly expensive and difficult to do a new trial, and there are some ethical issues associated with that. So if you have evidence which tells you your drug is not effective, you should not be exposing new patients to it. But also, you've gone to the effort of doing a trial versus drug A, and you know that drug B already has data versus drug A, so you sort of feel that there should be some information that we can use to compare our new drug to drug B. It might not be as good as a new trial, but we should have some information anyway. So broadly speaking, in this sort of situation there are two approaches. What I'm calling indirect analysis, or a full mixed treatment comparison. Now other terms are used, and one I particularly like is network meta-analysis, because that describes the situation well. But the main distinction is that one method, which I'm going to call indirect analysis for now, restricts itself to looking at one route within the evidence network. In our case, this is the route between our new drug and drug B via drug A. So that's an indirect analysis. In comparison, mixed treatment comparisons use data from across the network to make a single, internally coherent analysis in which all comparisons are calculated simultaneously. So if we look at this network, we might imagine that we could compare drug B and C, and our new drug and drug C, using the same approach that we've used to compare our new drug with drug B. And that somehow all of these comparisons should really be producing consistent estimates. Well, that's what a network meta-analysis does. So a network meta-analysis takes the data that we have, and then it uses it to produce effect estimates for each treatment relative to each other treatment within that network. So let's summarize that. In a direct comparison, we have an estimation of the relative treatment effect or other relative characteristic of one technology compared to another, informed only by head-to-head RCTs of those technologies. In an indirect comparison, we have an analysis comparing interventions that have not been compared directly within head-to-head randomized trials. And when we do mixed treatment comparisons or network meta-analyses, we have an analysis that compares two or more interventions using a combination of direct evidence from head-to-head trials, for example, and indirect evidence in one single analysis. So let's start with a simple indirect analysis. So here we have three treatments from our network. We've got our new drug, we've got drug A, which is the common comparator, and we have drug B. And we want to compare our new drug to drug B using drug A as an intermediate. Now we can't just take the scores for the new drug arm from our trial and compare them with the results from drug B in the other trial. If the reason for that's not clear, well, the answer is that it breaks randomization. So essentially we're taking RCT data and we're turning it into lower quality data, because each patient in our new drug versus B analysis did not have an equal chance of being in each arm. So if you're not used to dealing with trial data, that's not a very obvious point, but it is important and it is possible to demonstrate it. If you'd like to know more about the value of randomization and why we use comparative data, let me know and I'll discuss it in a separate session. The key point is that we should avoid comparing data from one arm in one trial with another arm in another trial. Instead, we use comparative data. In this case, we would use comparative data from our direct meta-analyses, and those data really do have to be appropriately sourced and reliable. So let's start with our direct meta-analyses. We've already calculated a pooled effect for our new drug versus A, so I've added that here. So our overall effect estimate was 2.381 with a standard error of 0.89. Now let's imagine that there's an existing meta-analysis of drug B versus drug A as well. So I've put the results in here. If I tell you that a higher score on our outcome is better, you might reasonably assume a couple of things. First of all, you might reasonably assume that the new drug is better than drug A. And in fact, our confidence intervals support that assertion. You might also assume that drug B is better than drug A, although we haven't actually demonstrated any clinical or statistical significance. Now, if you're feeling particularly bold, you may even claim that your new drug is better than drug B. So you might claim that this is better than this, because this is larger than this. And if you were forced to, you would probably guess that the difference between your new drug and drug B is 2.381 minus 1.879, which is 0.502. And in fact, this is exactly how indirect analyses work. Although this being statistics, we have to say it was rather more squiggles and Greek letters. So the point estimate that we've just calculated there, 0.502, that is correct. That is a correct indirect estimate. However, like most point estimates, as you'll come to discover, it is essentially meaningless without some context. In this case, we certainly need a confidence interval. And to get a confidence interval, we need a standard error. Luckily, we have the two standard errors from our original analyses. Now, in general, if we add or subtract two distributions, the resulting distribution has a variance that is the sum of the other two variances. If we use this to calculate our new standard error, sorry, I'm going to start this again. Unfortunately, the point estimate produced is, like most point estimates, essentially meaningless without some context. In this case, we certainly need a confidence interval. To get a confidence interval, we need a standard error. Luckily, we have the two standard errors from our original analyses. Now, in general, if we add or subtract two distributions, the resulting distribution has a variance that is the sum of the other two variances. We can use this to calculate our new standard error. And that's what we've done here. Finally, we can calculate our confidence interval from that standard error using the 1.96 key value that we used before. As you can see, there's considerable uncertainty around our effect estimate. And I think most of us would see that this intuitively reflects the additional uncertainty of indirect evidence. Because we're taking two sets of estimates, this one and this one, both of which have a known error associated with them, and we're potentially confounding that error. Now, as you may imagine, these equations need adapting for different outcome types, or the outcomes themselves need transforming. For example, we might use log odds ratios. But this is exactly the sort of transformation that you need to do with direct meta-analyses anyway. Now, it may not be immediately obvious, but it is technically possible to extend the evidence network beyond 3 treatments to obtain an estimated effect. However, as you can see from the formulae, the confidence intervals around the estimate of effect get larger very quickly. So if we had another drug in here, which was only compared to drug B, we could compare this other new drug to our existing new drug, but we'd be adding up variance along the way. And so our uncertainty increases very, very quickly indeed. There's also the risk that the populations we're looking at are not really similar. And that's not often talked about because it's a clinical issue rather than a statistical issue, but it's an important issue. And therefore, if treatments aren't part of a fairly close evidence network, they may be being used in slightly different circumstances. Your uncertainty in effect estimation is increased, and so it really becomes more difficult to make a robust argument around your effect. So whatever approach is used, and however many intermediate steps are used, me and my team prefer to use an internally developed and checked Excel-based calculator to ensure that the calculations we do are performed consistently and can be checked. The calculator we use also includes rules for commonly encountered variations in the standard procedure, for example to handle log odds ratios. Okay, now there are some fairly obvious, for the most part, assumptions and limitations to these methods. They're relatively simple and they can really be derived by thinking about the way that we're treating our data. So if we start with our limitations, first of all, if we have multiple paths that can provide our estimate, for example via drug C as well, so if we had another drug here and our new drug was compared to drug C and we could go via that, then we don't know which path to use. As a result, we can get inconsistent results using these types of indirect analysis. Also, due to the additive variance law, we can have a hard time achieving statistical significance even when our new drug is superior to drug B. In other words, indirect analyses suffer from limited statistical power. Okay, moving on to the assumptions. The assumptions that we have are really an extension of direct meta-analysis assumptions, in that we use the results of direct meta-analyses, so we need to assume that the studies included are measuring the same thing. That means statistical homogeneity, but also clinical homogeneity. And this assumption actually has to be extended somewhat so that we can assume that the patients in our new drug arm would have had the same response observed in the drug B arm if they'd been in that study. So if a patient in this study had magically been put into this study, that they would have a similar response to the patients that are already in this study. Essentially, we're saying that all the included patients and studies are effectively identical. Now that's quite a strong assumption and it can be difficult to assess it. The assumption is rather difficult to describe and has several names, but my preferred one is exchangeability of effect, because the assumption is that if you took any patient from any study in any arm and moved them into another arm or another study, they would respond in the same way as the patients already in that study and arm. Other people call it the similarity assumption, but I don't think that captures the strength of it. Alright, so I think that's enough about the assumptions and limitations of indirect analyses. What we're going to do now is move on to mixed treatment comparisons, or network meta-analyses. So these are becoming increasingly important in health technology assessment due to the number of treatments that may need to be considered and the desire to have a consistent interpretation of the available data. For example, if you work for the National Health Service in the UK, you want to choose between a group of drugs. So if you have a patient who has severe psychotic symptoms, you want to choose the most effective antipsychotic treatment or the most appropriate antipsychotic treatment for that patient. And that decision is not a series of comparisons between two drugs, it's the choice of a single drug from a whole selection of potential drugs, or of no drug. So if we return to our star-shaped network, you immediately see that our comparison of the new drug with drug B is entirely reliant on indirect evidence. Now, we can use mixed treatment comparison methods in this situation, but the results we get aren't really superior to a standard indirect analysis, and we don't really realise a lot of the benefits of a mixed treatment comparison. So, to get around that, let's add in some additional evidence. Okay, so now we have an additional study comparing drug B and our new drug directly. And in fact, this more closely resembles a lot of the real evidence networks that we see. Because you don't necessarily always have direct evidence comparing two drugs, but often you do. And sometimes you have indirect evidence and direct evidence. So now what we have are two potential sources of information on the comparative efficacy of our new drug and drug B. We have the direct route here, and the indirect route via drug A. Now a reasonable person might assume that if the indirect route produced a result that was very similar to the direct route, we might believe that the direct result is more credible. Now again, that's exactly how MTCs work. There are several ways of doing mixed treatment comparison analyses and a lot of ways of adjusting them, but I'm going to talk about a simplified version of the general approach we use. We tend to implement this in WinBUGS, which uses a Bayesian paradigm. Don't worry about that too much. We'll talk about Bayesian statistics in another session. But there are other frequentist approaches used as well. So we start with our estimate of effect and what effect we're looking at. As with our examples so far, we'll work on a continuous outcome. Now, as discussed earlier, we have to look at the difference between arms within studies so that we can preserve the randomization of our RCTs. To make this simpler, it's helpful to have a reference arm. Given that we have a common comparator, drug A, let's use that. Okay, so to formalize this, our study result, theta, are specific to study J and treatment arm K relative to our reference treatment, drug A. What this means is that mu here, mu J, is the study effect, and we're setting the treatment effect for drug A to 0, and the treatment effect for any given drug here is delta JK, so that's drug K in study J. So for example, the treatment effect of our new drug is a consequence of mu J, which is whatever the study effect is, plus the delta associated with our new drug in this particular study. Now to complete the random effects model, we need a distribution for our comparative treatment effect. This just shows that delta for each drug follows a normal distribution with mean D relative to the effect A, that's dA, and variance sigma squared. So if we treat the effect of A as 0, then that makes it fairly easy to just look at the effects of individual arms on their own. We don't always set the effect of drug A to 0, but we often do if it's a placebo arm. And that's really one of the most common situations that we have. So the model I'm using here is based on the model by Welton et al. And Nicky Welton and everyone else is referenced down here. I'm not going to go into a huge amount of detail on the specific statistical model that we use, because there are various other adaptations to it, and there's a whole series of training sessions available to try and explain those, and that really has to build up from quite simple statistical underpinnings. But the important thing here is that the effect that you observe in any arm is a consequence of a study effect and a treatment effect, and that you set some treatment effect, usually if it's placebo to 0, although you don't always have to do that. Okay, so essentially there are a number of approaches to solving this equation, or series of equations. We usually use a Bayesian approach through WinBUGS, and the Bayesian approach seems to be the most frequently reported. That's partly because things like WinBUGS have really made it hugely easier to do these sorts of analyses. It doesn't mean they're very easy, but they are relatively easy. There are now bits of code that you can use in other programs like SAS or in Stata even. Although I personally prefer WinBUGS because it forces you to explicitly state your statistical model. Now WinBUGS uses a simulation-based approach to calculate Bayesian posterior distributions. So, first of all, our model specifies our parameters. So in this case, the treatment effect of our reference treatment drug A is 0, with the study effect described by the parameter mu. The effect of each treatment nested within each study is delta. And the standard variation of the random effects is sigma. There. Okay. We then specify our prior distributions, which describe our beliefs about these parameters prior to the analysis. Because we're uncertain, and to avoid our prior beliefs driving our analysis, we tend to use what we call vague priors. On these plots, our priors are so vague that we can't even see their distribution. There's just a slight blue line at the bottom. And that's basically a very long distribution just squidged across the line. We then set our initial conditions. Because we're running a simulation, we need initial conditions to start it off. WinBUGS can do that automatically by picking from our priors, but we usually specify vaguely sensible initial conditions so that we don't have to run our simulation for too long before it finds a sensible result. In practice, I don't actually find that it makes as big a difference as it might with simple models. It's more when you get very complicated statistical models. So using these priors, WinBUGS then calculates what data we would expect to see and records whether it matches what we have observed. WinBUGS then chooses more values for our parameters, runs the analysis again and records whether it matches what we've observed. If we repeat that a large number of times, we get a likelihood distribution. This is simply a distribution that describes the likelihood of observing the results we actually see, given our priors. The red curves illustrate these likelihood distributions. The likelihood distribution is then used to update our prior distribution to give our posterior distribution, which describes what our new beliefs should be based on our model, our priors, and our observed data. The green curves illustrate this. So what you see is you see a great deal of uncertainty, a likelihood distribution that sort of says, well, this is how those two things interact, and then a posterior distribution, which is kind of a fusion of the two. Note that the green distributions rely on both the data we observe and our prior beliefs, and the way these are combined relies on the statistical model we use. Therefore, the validity of an analysis depends on assessing the validity of our data, the validity of our priors, and the validity of the statistical model we use. So the detail there doesn't necessarily matter too much unless you're actually going to be doing mixed treatment comparisons. But the general principles result in some assumptions. So the assumptions of mixed treatment comparisons are really just an extension of those for indirect analyses. The main advantage is that the results are consistent, at least within each outcome. This means that the data can be interpreted together more easily, which certainly helps with things like economic modelling. But it should also help with explaining the meaning of data to clinicians and patients, and overcoming some of that difficulty you get where you have data from various trials of various treatments that don't really appear to paint a consistent picture. The main disadvantage of mixed treatment comparisons is that they are comparatively complex statistically. In fact, I actually think the most complex thing is solving the equations. The equations themselves are not horrifically complicated, but the solutions to them do tend to be. It is great that the models are explicit, because this improves the transparency of analyses. But the method for deriving the results is not easy for non-experts to understand. Given that, an important part of any MTC is to explain it and to demonstrate the logical consistency of any results. Because without a detailed statistical understanding, it might be that the people reading your reports are unable to make a fully informed decision as to whether the analysis is valid. And so the only thing they can base it on is whether it fits with what they understand. So if you present your results in a way which is nice and clear, then people will get that warm fuzzy feeling that the analysis is appropriate. Okay, so that brings us on to describing analyses. Now, I've tried to avoid imposing a strict procedure for deciding whether to do an MTC or whether to do an indirect analysis or any other particular type of analysis. There are several reasons for that. First of all, it can be unclear whether an MTC is better because there's no simple way to determine whether trials are sufficiently similar to one another. So for example, even where you don't have statistical heterogeneity present, there might be some underlying clinical heterogeneity, and you may or you may not be concerned by that. Similarly, you may get statistical heterogeneity where you are aware of the source of that heterogeneity, and so you are able to account for it within your analysis. A good example of where you need to be cautious is what I call the fractured network, where the shape of the network may suggest that something odd is going on. So for the fractured network, it may suggest that there are two different indications. So often we get that where, so for example, in arthritis, you might have a methotrexate network, where all the treatments are used in combination with methotrexate, and one network where treatments are used on their own. And there'll be some trial data that connects those networks. But it would not necessarily be appropriate to compare patients that are treated with methotrexate with patients that are treated without methotrexate, because there may be some reason why some patients are treated with it and some aren't. A sparse network really describes where there's a lack of information content within the network. So you may be able to do multiple indirect analysis routes, and you may even want to aggregate those data into a consistent analysis, but most of the time it's going to be difficult to get any statistical significance because there's not enough data there, and so there's going to be a huge amount of uncertainty around the results. So the actual benefit of doing that whole involved analysis might be quite limited. Now we could potentially use various approaches from graph theory and things like that to classify evidence networks into particular types, but most of the time careful discussion around the real decision problem and business motivations for analyses allows us to give better advice than a dumb rule ever would. That doesn't mean there's no role for dumb rules, it's just we have to be a bit wary of them. Now in the past, people have tended to do direct analyses, then indirect analyses, then mixed treatment comparisons. Rather than being a scientifically robust approach, that really reflects the confidence that users have in the methods. most people working in health technology assessment are now comfortable with direct meta-analyses, and an increasing number are comfortable with indirect analyses. Often people are interested in mixed treatment comparisons as exploratory analyses, although that obviously introduces even more problems with multiple testing than normal. Therefore, we try and use simple rules of thumb that can be altered if an analysis requires it. So just on that, I've actually seen a huge increase in the use of mixed treatment comparisons and network meta-analyses recently, to the extent that people it's now fairly standard within health technology assessment. It's still not really standard more generally. So, for example, you don't necessarily see it that often in Cochrane reviews, which are really aimed at clinical users and the general public. It could be used more frequently in those situations, but it really needs to be explained in a way that makes it comprehensible to people. So we tend to do direct meta-analyses where there's a large body of direct evidence and we're interested in a single comparison. We tend to do indirect analyses where there's only indirect evidence and we're interested in a single comparison. And we tend to do mixed treatment comparisons where we have multiple analysis routes and where we're interested in networks of evidence, for example for model development. Now sadly, most evidence networks fall into the grey areas between these. So, you have a bit of the evidence network has quite a lot of data and other bits have less data. Also, many people want a large number of outcomes to be analysed. Now often the primary outcome of interest can be analysed using a mixed treatment comparison, but the secondary outcomes may be poorly reported, which in itself leads to problems of bias and sparse networks. Also, doing too many analyses is bad statistics. It creates a problem of multiple testing and the threat of cherry-picking data, either consciously or subconsciously. So, given all of that, our guidance is to state the decision problem, which is very easy if you're doing something like a submission to NICE in the UK, because they tell you the decision problem. Then determine the outcome of primary interest, and if there are secondary outcomes, explain how they fit into the argument, because ideally you'd include secondary and primary outcomes in one statistical model. It'd be quite complicated, but usually that at least is more clinically plausible. So then we move on to describing the evidence network, and we try and identify any reasons for patterns within the network. So if there's any unusual shapes within the network, so for example a fractured network or anything like that. We then check the clinical consistency of the network. We might move those around in a different order, but making sure that the studies are comparable. Then we decide on an appropriate analysis approach. So we don't start saying we have to analyse it this way. We look at the network to find out how we should analyse it. Importantly, we run the analyses after we've decided what the analysis approach is. We don't do all the different types of analysis we can and then choose the one that gives us the results we want, because that's bad statistics. So we run the analyses after we've decided what analysis approach we should take, and then we check for consistency in the results and look for statistical heterogeneity. So statistical heterogeneity might indicate that there's some clinical heterogeneity underlying our results that we haven't been able to pick up. And then finally we decide how to present our results. Now here I've just got two examples. The first example on the left we see quite frequently now, it's kind of standard, is that because we're using a simulation based approach in WinBUGS, the simulation can tell you how frequently each of the treatments comes out on top. And typically this is useful where you have data that are uncertain. So a clinician has to make a decision. They have to choose what treatment to use. And that's really regardless of whether there's a statistically significant difference. They need to know that they're sort of hedging their bets and they're more likely than not to be making the right decision. And the way that WinBUGS runs analyses allows us to come out with a sort of percentage estimate of, or percentage description of how frequently each drug comes up top. So in this one, drug A comes up top, most of the time. We wouldn't be like 95% certain that it's better than everything else, but 2/3 of the time it's better than the other treatments. Interestingly, there are some treatments which are roughly similar to placebo. So this is a fairly standard way of doing it. Another way of presenting data are to take indirect and direct evidence and maybe mixed treatment comparison evidence as well, and using the standard comparator, in this case drug A, produce a forest plot which has the direct and the indirect evidence alongside. Now what I like about this is it allows people to decide what sort of evidence they trust, and it also allows people to look at the consistency of evidence. Now that's not a really strictly robust statistical approach, but generally if you see that the direct and the indirect evidence agree, then you probably believe the estimate a little bit more. It also means that if somebody doesn't like mixed treatment comparisons, they've at least got something to base their decisions on. Now there are some other very, very cool ways of presenting data. I'm not going to go into them at the moment because they're really more about explaining the impact of results than, and some of them don't make the analysis any clearer. But they demonstrate the impact of it more clearly. Also, some of them are really very exciting, and I would want to do as a separate presentation on those. But these are just two approaches that you might want to consider. Okay, so in summary, direct meta-analyses are relatively simple, and single indirect analyses are as simple as direct meta-analyses, but require some additional assumptions. And both direct and indirect analyses can produce incoherent results across an evidence network. Mixed treatment comparisons produce internally coherent results, but depend on data and some assumptions of consistency. Often you can test those, but not always. Choosing between analytic approaches is often difficult, and interpreting the results can be difficult. Also, assessing the reliability of results can be difficult, particularly as we often find with newer treatments you have a limited evidence base. So the approach that I prefer to use, and my team likes to use, is to make all our analytic decisions explicit, explain them, and then show the results as clearly and as honestly as possible, so that the person making a decision is in a position to make an informed judgment as to how they should interpret the available data. Okay, so that's all I have for you today. If you have any questions, please do get in touch. I'd love to hear from you. We have other training available. If you have a particular request for training that you'd like to be made available, please let me know. Thank you.